We're very pleased to start off with Ryan O'Donnell. Ryan O'Donnell has been a professor at Carnegie Mellon University since 2006. He got his Ph.D. in the Department of Applied Math at MIT in 2003, and since then has gone on to get many grants and awards. He's an expert in quantum computation and information theory, and has literally written the book on algorithmic foundations and analysis of Boolean functions. Messed up the title, but I think we haven't written too many books, at least. And so with that, I'll hand it over to Ryan.
Thanks, Cynthia. Thanks for having me. It's so nice to be here. I was a postdoc in Seattle many, many years ago, so it's great to be back. If you get bored during the talk, I also made a little game where you can try to spot two depictions of Mount Rainier in the slides. Unfortunately, the weather is not correct to see the actual one, but I guess it's somewhere over there. OK, here's the plan for the talk. Part one is about quantum and maybe why you should care. The real reason is just that it's fun, but I'll tell you some other reason as well. Then I'll give you some kind of rant about comparing probability distributions. And then I'll tell you about how me and my co-author Steve, we tried to solve this quantum problem, but we accidentally improved the best known result for some classical problem. And then finally, we also solved some quantum problem, which I will tell you about at the end. OK, so part one, quantum. Why might you care about this? Well, let's say you need to model mathematically some random phenomenon that exists here. Then this guy Kolmogorov in 1933 told you exactly what you need to do. Mathematically, you just have some set of outcomes. And we'll only worry about finite sets, so d outcomes. And you get some probabilities. These are positive numbers that add up to 1. And you have some events, which are subsets of the outcomes. And that's it. Then you can do any probability you want. Sounds fine. But actually, it turns out you can't do every probabilistic thing you want. There's some actual random phenomena in our universe that are just not adequately modeled by these basic laws of probability. You need a generalized notion of probability to model all the stuff that's in our universe. And this generalization is some kind of non-commutative probability. So let me give you a little demonstration to try to convince you of this fact. Every single person does the same demonstration on YouTube, but I will also do the same demonstration because you can really do it with equipment that you can buy for $4. So I have here these pieces of plastic that are called polarizing filters. They're literally the things you get in the 3D glasses when you go to the movies. And you can get 3 of them, and you put them together. Let me put them together the right way, like this. OK, these 3 pieces of plastic. And then if you shoot a laser pointer through them, I don't know if we can see this. OK, it's not showing up very well, so you'll have to maybe take my word for it. I practice this and everything. You should never do a demo in real life. Maybe it's too dark in here. OK, anyway, you can try it yourself. If you shine this light through them, you'll see a tiny bit of light comes through. Actually, if you compare the intensity of the laser pointer itself to the amount of light that comes through when you shine it through these 3 things, it's 1/8 the intensity of the light comes through. OK, and it really is the case that for every photon, it gets past the first square with probability at half, and condition on that, it gets past the second one with probability at half, and it gets past the third one with probability at half. And that's why 1/8 of the light comes through. But then you can do the rest of the party trick, which is that you take this and you remove the one in the middle. And then when you shine the light through, 0 light comes through. And that sounds counterintuitive, right? You just took away one barrier and somehow less light comes through. It seems impossible. And it is impossible if you just model it with a regular old probability. But it's justifying the fact that there's some stuff that happens with everyday objects that are just not captured by the normal rules of probability. And in fact, what's really going on here is this source of photons is a non-commutative probability distribution that's modeled by this matrix. And these are non-commutative events that are modeled by these matrices. And it's just a fact about matrix multiplication that this matrix H times this matrix V is the 0 matrix. And that's why if you just have this first filter and the third filter, no light comes through. But H times D times V, if you can do the little computation, this is not the 0 matrix. And that's why some light comes through when you actually shine the laser through all 3 of them. And it's because one of the properties of matrices is they don't commute. Matrix multiplication doesn't commute. And so this is possible. Yeah, so this is a little illustration of why you really need this generalization of the laws of probability to model the random stuff that happens in our universe. OK, so these non-commutative probability distributions are also sometimes called quantum states. because they actually model the states of qubits. So this is actually every photon coming out of this, the polarization state of every photon coming out of this laser pointer is like a qubit. And it's represented by this kind of generalization of a probability distribution. And these non-commutative events are also called quantum effects or quantum measurements. So yeah, this is just a little summary about how actually like another name for non-commutative probability is quantum mechanics. Or you can think that quantum mechanics is really just like a generalization of the laws of probabilities that applies to like all the objects in our universe. And yeah, it's just like some generalization of probability where everything, instead of being like a vector of probabilities, now it's like a matrix. So all the objects are matrices. And yeah, so it's kind of like probability 2.0. So if you like probability, then like you should like quantum even better. So that's how I kind of got into it, in fact. And so for me, like, normally when you hear about quantum computing, you're like, oh, we're supposed to get these cool quantum computers, and like maybe they'll solve traffic, and they'll like cure cancer, and they'll prevent climate change, which is none of that is true. And for me, like, I'm not interested in like this thing, like using quantum computers to try to solve classical problems faster. What I'm interested in is solving quantum problems like not slower. So like all these quantum problems are like generalizations of problems about probability in computing. And so therefore they're harder. And so therefore the challenge is to still solve them not much worse than you solve the analogous classical problems. OK, so that's part one about why you might be interested in quantum. But actually, for the most part of the talk, since I don't want to assume like you know anything about quantum, I'm mostly going to talk about classical things, which are analogues of quantum problems. So now I'll go on like a little rant about, it's not much of a rant, but how to compare two probability distributions. Because I'm going to talk about some like learning problems, and when you talk about learning problems, you need to like talk about whether probability distributions are close or far, and I want to understand what that means. So here's maybe the most basic of all possible like statistical or learning problems. There's like some unknown probability distribution P on D outcomes, and you get a bunch of samples from it, and your task is to estimate the probability distribution P. You're supposed to estimate or output your own probability distribution Q that's somehow close to P. That's the task. But yeah, and I want to dive into like what does this mean, close? What does it mean for two probability distributions to be close? And what it means really depends on like who you like to ask. So there's actually different ways you can measure how close two probability distributions are, and like different groups of people that love them, these different things in different ways. So here's how I split it up. So one way is this method called total variation distance. This is extremely popular with theoretical computer scientists. They're obsessed with total variation distance. They would never dream of like comparing two probability distributions in any other way. This is all it means to them. There's another kind that's called Hellinger distance, or Hellinger squared distance. And secretly, although they don't know it, like people who are into quantum really love Hellinger distance because it's exactly this thing that they call quantum fidelity or quantum infidelity. It's exactly the quantum analog of Hellinger distance. So secretly, they really love this other way, Hellinger. I like it too, by the way. And then, like in information theory, they really love this thing KL divergence, or relative entropy. It has some information theoretic meaning. And then there's another one called chi-square divergence, which mainly only statisticians talk about, but we're going to talk about it in this lecture today. So yeah.
What about optimal transfer results?
Oh, I don't know. You tell me. What did they like the best? Bregman divergences? What's that?
Wasserstein?
Oh, Wasserstein differences. So that assumes, good question. Here, all my probability distributions are just on like the numbers 1 through D, and I don't assume that these outcomes bear any relationship to one another. Moreover, the things that you have a probability distribution over has like some notion of distance or a metric on it, then like, yeah, there's even more glorious possible distance measures like Wasserstein distance you could care about. So in fact, this is not even all of them. This is what like, I really love the statistics notes of this guy, Yihong Wu, and he calls these the big four, but there's way more than just the four, but let's stick to four. That's all it will fit on one slide. Right. The good thing about all these things is they have a natural meaning, and therefore like you need to like use different ones at different times, I feel. So like total variation distance between two distributions P and Q, that's like relevant for this question. Like if I give you one sample from a distribution which is either P or Q, and you have to guess, did this one sample come from P or Q? Total variation distance is about like how well you can guess. The Hellinger distance is about like a question that I think theoretical computer scientists should have loved, which is like, what if you're given like lots of samples and they're all coming from P or they're all coming from Q? How many samples do you need to confidently judge whether they're coming from P or Q? It's literally exactly the reciprocal of this Hellinger squared. This KL divergence has some like information theoretic interpretations. And this chi-squared one, which we're going to talk about later, is very relevant for this other task called hypothesis testing, which is you have some distribution Q written down on a piece of paper that you know about, and you're getting samples from an unknown distribution P. You're trying to decide, is this unknown distribution P, is it equal to my hypothesis Q, or is it like far from my hypothesis Q? And chi-squared is very relevant for this problem.
Why didn't you use the hypothesis testing calculation for KL divergence here? That would fit the slide a little.
Well, like for one sample?
No, for given n samples from each
I don't think it's like so relevant. Like total variation distance doesn't tensorize.
No, the KL divergence.
Oh, KL divergence. Yeah. Well, all three of these bottom ones tensorize, especially these two. So they're very relevant when you have multiple samples. Yeah, I couldn't think of the pithiest one to say for KL. Maybe you could think of the. Yeah, I guess it's related to the rate of the error rate. Yeah, so there's plenty of reasons to love different ones of these, and I think you should just choose the right one for the job is maybe the end of the rant. For the rest of the time, I'm actually going to look at the square of this, not because it's natural, but like if you look at the square of this, then these things are perfectly ordered. Maybe there's some factors of 2 or something here that I'm not going to care about, but otherwise they're perfectly ordered in this like inequalities. And I should also mention that these ones are actual metrics, and they're bounded between 0 and 1. These ones are not even symmetric between interchanging P and Q, and they can be as large as infinity. Yeah, so because they're perfectly ordered, like this is like the loosest one. So maybe like if 2 distributions are epsilon close in total variation distance squared, you can call them close. And here they're like super close, and here they're super duper close, and here with chi-squared they're like ridiculously close. So sometimes I'll use this terminology, this very sophisticated terminology in the talk. OK. And I'm not going to define all of them, but I'll define like a couple of them, in particular the chi-squared one that we're going to talk about. But how can you compare 2 distributions P and Q? For every outcome j, you can look at the ratio between pj and qj, and ideally this ratio would be close to 1. So we can define error sub j to be the difference of this ratio from 1. And then like the total variation distance squared is like the square of the expected value of this ratio when j is drawn from q. Whereas chi-squared is like the expected value of the square. So you can therefore see by Cauchy-Schwarz that this one is at most this one. And the other two in the middle, I put some faded out text because you can read it if you really want, but I'm not going to go over these definitions. And that's actually a funny thing to do, actually, to take the square, because usually this number is smaller than 1, but like if the ratio between P to Q is like 50, which could happen, then like this error is like 49, and then you're squaring that. It's you can see why this one's quite punitive, because like this error squared could be a tremendously large number potentially. In any case, I want to focus on this alternate formula. If you just plug this into this, you'll get this alternate formula. And in this formula, you see that the chi-square divergence between P and Q, it almost looks the same as like the L2 squared difference. So if you cover this up, this would be like the L2 squared difference between P and Q, which is even like a 5th closeness measure that I didn't put on the previous slide. So it's like this, except it has like a penalty factor. For the L2 squared term corresponding to j, you penalize it, or you like make it amplify it by the reciprocal of qj. Okay, so this is therefore potentially bigger, and it can get like it can make you nervously large if qj is really small. Okay. So that's actually the end of my little story about how there's different ways to compare probability distributions, and it's good to keep different ones in mind. But since we're here, let me tell you precisely about this task, the task of estimating a probability distribution from samples. There's an obvious algorithm for this. In fact, you might not even like occur to you that like you should think about algorithms here, because if I get like n samples from an unknown probability distribution and I have to output an estimate, what else are you going to do except output the empirical distribution? So you would output like qj is xj over n, where xj is the number of times you saw outcome j. That seems like the natural thing to do. So xj is a binomial random variable. And you can ask, how well does this do? To analyze this, let's look at the expected L2 squared error, which is a funny thing to do because we don't actually care about this L2 squared error per se. It's not one of the 4 interesting ones. But it's definitely the easiest one to compute with because like it's a polynomial of degree 2 in both P and Q. So it's extremely pleasant. It doesn't have any absolute values or anything. So we can look at this quantity. Okay, so it's got this expression. Here, by the way, p is fixed and q is like a random variable. And in fact, actually, this random variable qj, its mean is pj. So this is actually the variance of the random variable qj. And qj is just a binomial random variable divided by n. So we know the formula for the binomial variance. It's like p times 1 minus p. And therefore, if you sum this up, because the sum of pj's is at most 1, this quantity is at most 1 over n. Okay? And that's great. It's a really simple formula. It's a very simple fact. It says that the expected L2 squared error of this simple algorithm is bounded by 1 over n. Okay, or to turn it around on its head, you could say that, okay, by Markov's inequality, this means that with high probability, the L2 squared error is order 1 over n. And therefore, if you want this quantity to be epsilon, it's sufficient for n to be 1 over epsilon. Okay, so if you want the L2 squared error of your estimate to be smaller than epsilon, you need something like 1 over epsilon many samples. Okay, that's nice. And it's kind of cool that it doesn't even depend on d, the number of outcomes. But as I mentioned, we don't really care about L2 squared. We care about one of these other ways of measuring distances. But you can use this to get the results in this area. So by Cauchy-Schwarz, the total variation distance is basically the L1 norm of the distance between p and q. So the total variation squared is at most the L1 squared. And Cauchy-Schwarz tells you that's at most d times the L2 squared error. And so if you want the total variation distance squared error to be epsilon, then it's like you need to replace epsilon by epsilon over d. Okay, so we can get this kind of fact that the sample complexity for getting epsilon total variation distance squared error is bounded by the complexity of getting L2 squared error that's like epsilon over d, which is d over epsilon. And okay, in summary, that means this. If you want to learn an unknown distribution with total variation error squared epsilon, then d over epsilon samples suffice. And this is kind of like the most well-known basic fact about learning an unknown probability distribution. Okay, it has a simple proof. But what if that's not good enough for you? What if total variation, that was like the most loose definition of closeness. What if you want something more? Like what if you want your estimate to be ridiculously close to the truth? What if you want chi-squared error at most epsilon? You can have it. That's the good news. It turns out, like with basically the same number of samples, you can get a distribution that has like this much, much better closeness guarantee. And there's two proofs of this that I can tell you about. One is very elegant and simple. It appears in this paper by Kamat et al. From 2015. It's so short that it's hard for me to imagine this is the first place it appears, but it's the first place I know it appearing. And then there's another proof, which is like extremely grungy and like loses log factors, and that appears only in these slides. You might wonder why I would tell you about this terrible proof with the same results. I guess maybe you can figure it out. It's because it's the one that's going to work in the quantum case. But let me first tell you basically tell you the first proof. It's almost as you do the same thing. You almost do the obvious algorithm. But actually, you shouldn't do the obvious algorithm because chi-squared divergence has this property that, like, if you're not careful, the chi-squared divergence between your estimate and the truth can be infinity. If you output like some qj to be 0, your estimate is 0 probability, but there's like an infinitesimal amount of true probability on that one, then the formula gives you infinity. So you shouldn't do that. But to get around this, what you can do is like fictitiously start all your counts at 1 rather than 0. And then do the obvious algorithm. And the analysis is basically the same. You can write down, this expression, expected value of the chi-square divergence between the truth and your estimate. And now it's a little bit trickier. It's not just the variance of some random variable, but it's like the expectation of some fraction where the numerator and denominator are some binomial random variable. And if you have a little bit of probability practice, you can just work out like literally an explicit formula in terms of all the probabilities p. And the formula is basically this, d minus 1 over n plus 1. So it's bounded by d over n. And that's it. Then you're like, great. The error, if I want the error to be like epsilon, then I need the number of samples n to be like d over epsilon. And that's it. So that's the whole analysis of that. And it gives you like a much better guarantee for the same number of samples. OK. So now I'm going to tell you about the disgusting gross proof of the same thing. This is like the most technical part of the talk. So like you can hang in here for the next like 4 slides, then you can relax a bit for the remaining slides. So I'm going to tell you like a different way to get an estimation algorithm for an unknown p that's good in chi-squared divergence. And here's how it goes. So before I showed you the chi-squared algorithm, we looked at this very, very simple L2 squared algorithm. And if you're going to be using d over epsilon samples, the L2 squared algorithm's a number of samples was just the reciprocal of the accuracy. So if you're going to be using this many samples, you can run this L2 squared algorithm and get back a very accurate estimate that has error epsilon over d in L2 squared. And maybe that's already pretty good. OK, once you do this, this is an extremely minor step, but just like rename the outcomes so that your estimates are in descending order. Q1 is bigger than Q2 and so forth. And so your estimates might look like this. So like here is my picture of what you might have estimated Q1, Q2, Q3, all the way to QD. And your estimate is like 0.3, 0.2, 0.05, dot, 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 dot. Maybe the last few are 0. And it's a pretty good estimate for the distribution P. OK, so now what you should do is you're going to freeze all these estimates where your estimate is at least 1 over d, basically, 1 over 4 times d. And you're kind of like declare to the world, this is going to be my final estimate for all these probabilities. I'm going to try to refine these ones later, but this will be my final estimate for all these probabilities, the ones that are at least 1 over 4d. And given that you declared like these are going to be my final estimates for these ones, you can already pre-compute like how much that's going to cost you in chi-squared error. And you can go back to this formula. They're going to contribute. It's like the sum over all these frozen outcomes j. Here's like the L2 squared bound, but like times this penalty factor, which is, if you recall, is like 1 over qj. Now, because you're only freezing the ones where qj is at least 1 over 4d, that means the reciprocal, the penalty factor, is at most 4d. So this is going to be at most 4d. And then actually by your L2 squared guarantee that the sum of this L2 squared error over all the j's is at most epsilon over d. So in particular, over just the frozen j's, it's at most epsilon over d. And you can afford this, because this, if you multiply it out, it's order epsilon, which is your final target error. So good. So this error is not too much. And you've kind of made like some amount of progress here in learning the probabilities. Now, all the other qj's are smaller than 1 over 4d. And if it's not very hard to show that like your qj's are sufficiently reasonably accurate that the remaining pj's are also basically at most 1 over 4d. So let's say 1 over 2d. So all the remaining probabilities are at most 1 over 2d. So if you sum up all the unfrozen probabilities, there's at most d of them. So they add up to at most a half. Okay, so the remaining probability mass that you're going to try to refine your estimate on is only at most half the probability mass. And now there's like maybe like a kind of obvious plan you'll try. So what happened so far is that like, OK, you used d over epsilon samples, which is basically your budget. You froze some of your estimates. And the amount of chi-squared error you incurred so far is like order epsilon, which is OK. And the remaining unfrozen probability mass is at most a half. So the natural plan is to sort of repeat this, whatever just happened here, like logarithmically many times. And I'll come back to this in a moment. But assuming you can like do that, then kind of the obvious thing will happen. Like you'll do some more work. You'll do another round of estimates. You'll freeze some more estimates. The remaining unfrozen probability mass will go down to a quarter. And then you'll get some more estimates. It'll go down to an eighth and a 16th and so forth. And after logarithmically many rounds of this, the remaining probability mass will be very, very small, smaller than like epsilon over d. And then it's not too hard to show that like, OK, you shouldn't set your remaining estimates to 0. That's a dumb move. But like if you set them to like epsilon over d, then there's a very simple calculation that shows that like if they're already this small and you set your estimates to this, that also incurs at most epsilon chi-squared error. OK, so what it means is that like assuming we fill in exactly what this means to repeat this step, you've done basically d over epsilon samples times a logarithmic factor. And the chi-squared error you got was basically epsilon, again, maybe times a logarithmic factor. So basically, you've got the desired result of d over epsilon samples to get epsilon error up to like maybe 2 logarithmic factors.
So in doing this, when you've got, you see a frozen value, just ignore it. Is that the basic idea?
Mm-hmm. Yeah. So exactly as Paul says, like the only thing to fill in is like how exactly, what does it mean to like do this or like to refine the unfrozen part? And it's just as Paul anticipated. Say we got to like the kth stage and like the unfrozen probability mass is at most 2 to the minus k. I guess you should actually estimate it so you know roughly what it is. But let's just say it's like 2 to the minus k. Well, you can like sample from this distribution like p conditioned on the unfrozen guy. It's just the conditional probability that you get an unfrozen outcome. You can kind of sample from it yourself, but there's like a slowdown factor of 1 over alpha because the probability you see like a draw from the unfrozen things is like alpha. So you kind of lose a factor of 1 over alpha time-wise when you're trying to sample from this unfrozen distribution. OK. Now your budget is d over epsilon samples. So with this, given that you're going to get the slowdown factor of 1 over alpha, if you use the L2 squared error estimator, your estimate of this unfrozen condition distribution will only have this worse error of epsilon over d alpha. And alpha is a small number, right? So this is bigger than epsilon over d. So it looks bad because you have like worse error here. But somehow it's actually better. It's actually good. Because let's just go over this one line of math here. To say that your L2 squared error is this much, epsilon over d alpha, for your estimate of the unfrozen part is to say that, OK, this is the L2 squared error. This is your estimate. And this is the probability of the jth one in the condition distribution. It's the original probability divided by alpha, the unfrozen probability mass. So this is what your L2 squared learner with rejection sampling gets here. And then you just multiply this equation by alpha squared. And on the right, you get the alpha comes up to the numerator. And on the left, it cancels out this alpha on the inside. And what you get is that these numbers, alpha times rj, are like a good L2 squared estimator for the unfrozen pj's. And the error is like alpha times epsilon over d. And that's like good. It's like better than epsilon over d because alpha is small. And that's particularly good because like if we take these numbers as our new estimators for the unfrozen j's, like our new q's to fill in here, since this error is smaller, we can tolerate like a larger penalty factor when we're moving from this L2 squared estimate to chi-squared estimate. We can tolerate a penalty factor not just like 4 over d like before, but like 4 over d or 4d over alpha. Like this alpha can cancel out this alpha. Which means that like it's OK to freeze all the new qj's all the way down to the reciprocal of this, which is like alpha over 4d. So in this kth round where there's alpha probability less, we start freezing things as long as their probability is at least alpha over 4d. And that's basically it, because then the remaining qj's are smaller than this. The remaining pj's are also more or less smaller than this. And there's at most d of them. So if you sum up the remaining unfrozen probabilities, it's at most alpha over 2. And you kind of got to the next stage. OK.
That crazy, right? Like you slow down by 1 over alpha, but your relative error also gets better by alpha because you only limit alpha a fraction of the mass. So
yeah, it's not too crazy. Yeah. But like somehow, I don't know, I was surprised when we noticed this the first time. Like it seems that like as you're going along, it's probably getting like harder and harder to estimate these small quantities, but somehow not really. I guess you have, in some sense, you don't need to estimate them quite as well. OK. So the proof summary is with, OK, twiddle of d over epsilon samples, you can estimate an unknown distribution to chi-squared closeness epsilon. And maybe the one thing to take away for the last part of the talk is that this is actually like a black box reduction from L2 squared estimation, which is much easier, actually. It says if you want to get chi-squared accuracy epsilon, it basically suffices to get L2 squared, to have a routine that gets L2 squared accuracy epsilon over d. And then there's some polylog factors. So, OK, that's good to know. OK, part 3. So Steve and I, my co-author Steve Flamier, we're like trying to solve some quantum problem. And you don't have to pay attention to what it is. I just put this up here for color to like tell the story. But like, here's a classical problem. Say you're trying to learn like an unknown probability distribution on n bits, but it's not a general distribution. It's like a Markov random field where the graph is a tree, whatever that means. It's some distribution on a bunch of bits. But it's not a completely general distribution. In the 60s, like Chow-Kong Chow and this Liu gave a simple algorithm, the Chow-Liu algorithm, that does well at learning such things. And they showed that if you have infinitely many samples, then this learner is perfect. It learns the tree perfectly. That's good, but I guess eventually in real life we don't have infinitely many samples. So in 2021, these people, Bhattacharya, Gayan, Price, and Vinod Chandran, were like, what if we have a finite number of samples? What kind of error can we get? And I think also Daskalakis and one of his students had a related paper. And whatever, for this problem, they showed you could do it with something like n over epsilon samples. And it's particularly nice that they had just epsilon in the denominator, whatever epsilon is. And like Steve and I were like, oh, let's do the quantum version of this. It's like a whole probability 2.0 phenomenon. Like somebody did something with classical probability, try to do the same thing with quantum probability. And I think it's maybe relevant for if you're trying to build a little quantum system and learn something about it. OK, so we looked into this paper. And maybe a key aspect of this paper and like a key aspect of these special probability distributions is this. In this model, if you have two bits like A and B, these circles are bits, and you have this vertex C in between them, then the bits A and B are independent, conditioned on any outcome for C. That's like the nature of these distributions. As I said, this is all just for color, so you don't need to understand it precisely. In other words, like the mutual information between bits A and B is 0, conditioned on any value for the middle bit C. And in their paper, one component of it is discovering what the tree is, and then later you have to also learn the parameters associated to the tree. But for the part where they discover the tree, they do it by developing like a little test to test if two bits that you can get samples from are independent or not independent, or in fact far from being independent. And so this was like a key kind of component in their analysis, that if you're just getting samples from two bits, A and B, and you want to test that accepts if they're independent and rejects if their mutual information is bigger than epsilon, which is kind of like they're far from being independent, they had a statistical test for that. They used something like 1 over epsilon many samples. And that's nice. And in fact, that was kind of cool. It solved some recent open problem by Kenan and others. Here's actually what they proved more generally. So what I told you there was about if you're getting samples from two bits. But they're also like, OK, what if you're getting samples from two like random variables over a larger domain, like of size d, like we were talking about before? And more precisely, they showed this. If you have something like d squared over epsilon many samples from a distribution on like A cross B, where A and B are of size d, then their algorithm, if the marginals P, A, and PB are independent, it outputs yes with high probability. And if the mutual information between A and B is bigger than epsilon, it like detects that with high probability. And one thing that Steve and I did is like prove the quantum version of this, or prove the quantum case of this. Though actually, we didn't finally get everything we wanted because we got stuck on the conditional mutual information version of this problem, which was really easy for Bhattacharya et al. But somehow this conditional mutual information was very hard for us. So we kind of just stopped here. Yeah, so that's what I'll eventually tell you about. But then after we wrote down our proof, in the quantum case, we looked back like, oh, what if you just specialize this to the classical case? And it turned out we got like the same result, but with like a better sample complexity by some factor of d. So that's like another, I don't know, maybe like bonus of studying quantum. Sometimes you can like accidentally get better classical results too. OK. And I'll tell you a little bit about how our quantum or classical version of this independence testing problem works. But first I need to mention this key ingredient, which is called hypothesis testing. I mentioned it a little bit before. So hypothesis testing is this problem. You have in your hands like a fixed probability distribution Q that you know. It's written on a piece of paper. And maybe it's like the null hypothesis. And you get samples from an unknown distribution P, and you're like wanting to like test the, what is it, reject the null hypothesis. You want to like, accept if P equals Q, or reject if P is far from being Q. And the exact sample complexity of this problem was like only worked out like surprisingly recently in these papers by like Acharya and Daskalakis, Kamat et al. And some others. And basically, it was understood that the correct algorithm for this problem is to empirically estimate the chi-square divergence between the unknown distribution P and the known distribution Q. And the reason this is actually such a good idea is like once Q is considered fixed, if you remember the formula, it was basically the L2 squared distance with this penalty factor, which is 1 over Q. But if Q is fixed, then those are just constants. So this expression is just a polynomial of degree 2 in the P's. And so it's very easy to estimate and analyze. And anyway, these papers showed the following theorems, that you can solve this hypothesis testing problem basically with square root d over epsilon samples. And that's cool. This is like much more efficient than the task of learning P, which required like d over epsilon samples. And that's because you don't need to learn the whole distribution P. You just need to learn, like, is it Q or is it far from Q? And if it's far from Q, you don't have to waste time learning exactly in which weird way it's far from Q. You can just reject it. But because of this, like, it has this sort of slightly finicky theorem statement. This algorithm will accept if P is like ridiculously close to Q. They have close chi-square divergence. And it will reject if P is not super close to Q. They have far Hellinger distance. But it just turns out to be the right result. OK. And in this paper I wrote with Badescu and John Wright, we did the quantum version of this problem and kind of got the same result. The sample complexity for the quantum generalization of this problem had complexity d over epsilon. And this is sort of an example of doing the quantum problem like not worse. Because you might remember I said in the quantum probability, like everything is a matrix. So like a probability distribution over d outcomes is like d numbers. And you get sample complexity square root d. The quantum version of a probability distribution is like a d by d matrix. So there's like d squared numbers. So the square root of that is d. So this is actually kind of the right bound here. And it's an example of trying to solve the quantum version of the problem like not worse than you did in the classical case. Yep.
I'm a little confused about you said the correct algorithm is to empirically estimate something. What are you trying to do?
So the original papers for this, because they were written by like theoretical computer scientists or motivated them, they were like, oh, in the accept case, you should accept if P literally equals Q. And you should reject if P is far from Q in total variation distance. And basically in this first paper, they like presented like, oh, we managed to solve that problem with this sample complexity. But if you read the paper, they do it by like exactly doing this and solving this much, well, a priori more difficult problem. So they really do this, and then they're like, oh, I can solve this easier problem automatically.
Is there a sense in which I can think about this as canonical for one-sided hypothesis testing, like in the noisy setup?
I don't know what canonical means. I'm not maybe enough of a statistics expert to say. I mean, I do know that like this sample complexity is tight, even if you only care about the original problem of like exactly equal versus total variation distance squared. But I don't exactly know what is meant by canonical. And in statistics, they're also really interested in like what is with high probability, like if you want failure probability delta.
Like you accept a null hypothesis is probably going to 1 as the number of samples goes to infinity. That's one side. And then you just want to get the error exponent.
Yeah. So this is another like distinction. Computer scientists are always like, oh, we'll just get 2/3 probability of success, and then we can repeat like and use the median trick and dial that down to log 1 over delta. And statisticians are like, we're going to fix all the parameters other than delta and like really care about the rate at which your success probability goes to 1. So in that level of refinement, I don't exactly know what is the best story. OK, so at a very high level, like now that we have this like hypothesis testing thing in the bank, which we do since 2017, here's what Steve and I thought about this independence testing problem. Okay, so remember the task is you're given samples from a distribution P on like with an A part and a B part, and you want to know if the marginals are independent or far from independent. And here's basically the complete sketch. So step one is you get samples from P, but you can just discard half of them and get samples from the marginal if you want. So learn both of the marginals, PA and PB, to like ridiculously good closeness, forming estimates QA and QB. And by that I mean get like chi-squared error that's like, I don't know, a bit smaller than epsilon. Okay, and that costs d over epsilon samples, as we saw. And this chi-squared is basically additive under taking product, so it means that if you take the product of your estimates, Q is like QA cross QB, then this immediately tells you that the chi-squared distance between Q and the true product of the marginals is at most epsilon. And now, really, what are you trying to test? You're trying to test if P, the whole bipartite distribution, equals the product of its marginals. And now you're like, I basically know the product of its marginals, so I can do like hypothesis testing with P. I'll consider this Q, which is QA cross QB, to be like known. This thing I just learned, I consider it to be the known distribution, and I want to just test if P equals this. I really want to test if P equals PA cross PB. And the sample complexity for this, well, P actually has domain size d squared, so it's square root of d squared over epsilon, so this is also d over epsilon. And that's basically it. I mean, you have to like remember what the problem is and fit things in. And actually, there's one more step, because the hypothesis testing tells you something about the Hellinger distance, but we really want something about the mutual information. But Hellinger distance and mutual information are kind of almost the same, so there's like a little lemma that helps you bridge the gap there at the expense of a log factor. You don't have to really follow the details, but like the one thing I really want to emphasize here is that for this application, the mutual information tester, because the hypothesis testing part really wants like its hypothesis about chi-squared closeness, you really, in this first step, you really need to learn the marginals to like ridiculous good closeness. You really need to learn them to chi-squared accuracy in step one. Which is why I spent some time telling you that you could do even chi-squared learning with this sample complexity d over epsilon. And Steve and I wanted to do the quantum version of this problem. So actually, the quantum version of hypothesis testing was already known, but what wasn't known was the quantum version of learning a distribution, like a quantum distribution, to this ridiculous good chi-squared closeness. So for the application, we would want to get that result with d squared over epsilon samples. So that's what part 4 is about. We managed to solve this, and this is like maybe the main technical part in our paper. But yeah, now we have to ask ourselves, how much time do we have? Because part 4 takes 12 minutes, and like that's kind of pushing it. We can also stop halfway through. It takes 6 minutes. Maybe we should do the 6-minute version. Okay. Actually, we could skip this whole thing, and like the real story is it's basically the same as the classical case. But I'll give you 6 minutes of talk about it, and then we'll call it quits. So estimating a quantum state. What is a quantum state? I kind of told you before. It's kind of a non-commutative probability distribution over d things. It's also called the mixed state of a qubit. And whereas a probability distribution is like d positive numbers that add up to 1, a quantum state is a d by d positive semi-definite matrix whose eigenvalues add up to 1. It's just what it is in this generalization. And actually, that means it has non-negative eigenvalues that add up to 1. So that part is kind of like a probability distribution. And so you can also think of like a quantum state, a quantum distribution, as a probability distribution over d orthonormal vectors. So now like the outcomes are not just like the abstract numbers 1 through d, but they're like some d vectors in d-dimensional space. So that's a quantum state. And you can ask the same ranty question, like, oh, if you want to learn a quantum state or estimate a quantum state, like, what does it mean for your estimate to be close? And similarly, there's like at least 4 different ways you can compare them, and they're like in perfect analogy to the classical ones. There's trace distance, which is exactly the same as like total variation distance. It's the L1 distance. There's like infidelity, which is the one quantum people really love. It's the analog of Hellinger squared. They write S for the quantum relative entropy, and there's some kind of chi-square divergence. So there's all these different ways to compare probability quantum states as well. And again, they're like perfectly ordered like this. Like this is the laxest one, and this is like the most stringent one. And okay, so just to remember the parallels, remember for like a classical probability distribution P on D outcomes, there's this super simple algorithm that got L2 squared error epsilon with 1 over epsilon many samples. The quantum case is harder. So there is an algorithm that gets L2 squared error epsilon using D over epsilon samples. And that's actually tight. And the L2 squared error for quantum states, again, it's like a fifth thing. It's literally this. It's the Frobenius norm squared. It's just the L2 squared difference of all the D squared entries. Unfortunately, it's not so easy. The only proof I know of this is with John Wright from 2016, uses like a lot of representation theory. If you don't mind getting a worse bound, D squared over epsilon, then this paper of these 3 people from 2014 is easier. But anyway, that's all which is to say, like in 2016, we knew how to get like a good algorithm for learning quantum states in L2 squared distance. And you might remember this proof I showed was like a black box reduction from L2 squared learning to this more stringent, ridiculous chi-squared learning. And that's basically what's going to go on here. Yeah, you can use the same Cauchy-Schwarz argument to immediately get that, like, once you have L2 squared learning, you can get like the L1 learning, this trace distance learning that actually has a meaning and people care about. You basically take this expression and replace epsilon with epsilon over D. And this shows that you can learn an unknown quantum state to the analog of trace distance squared with D squared over epsilon samples. And again, this is sort of like the right tight bound because like it's a D by D matrix, so there's kind of like D parameters. So D squared over epsilon is a plausible number of samples.
I mean, can you prove that you really need that many samples?
Yes, there are lower bounds that exactly match this, yeah. Yeah, so that was about trace distance squared, but you're like, what about stronger metrics? And this paper of like Ha, Harrow, G, Wu, and Yu from the same time, basically the same sample complexity, just a log factor, and this like super closeness of infidelity at most epsilon. So that was great. Used some more representation theory. And then John and I were like, oh, let's work even harder. And we did some more representation theory. But like, we couldn't get beyond this. We couldn't get like super duper closeness or ridiculous closeness. And like, there seemed to be like a big gap here. Because like, these are the ones that are like bounded metrics. And these are the ones that like can be infinity. And so like, I really thought like, maybe it's not even possible to get these in the quantum setting. But it's possible. So this is what Steve and I also did. We showed that basically the same sample complexity as before, D squared over epsilon. You can learn with this ridiculous closeness epsilon. And it's exactly by black box reduction from this result in the same way we saw black box reduction in the classical case. And yeah, that's it. That's maybe my 6-minute version of this. So it's the same grungy reduction. And in order to like be convinced of that, you just need to know the definition of chi-square divergence for the quantum states, which I'll skip. But you can look at the slides real fast as I click through them. It's basically the same L2 squared thing, but there's like a penalty factor. There's this picture. And the freezing now looks like this. As you're going along, you're trying to learn a matrix. And as you're going along, you kind of like freeze like this top left gamma shape of the matrix and like recurse on these like submatrices. So if you got the classical version, and like I told you the definition of chi-square divergence of the quantum case, then maybe you too would recover this same algorithm.
Back for 1 second.
Okay, sure. So I'll say this for you. This is unitarily invariant. So in order to define this, it suffices to define it when sigma is a diagonal matrix.
I understand what you're looking at.
Okay. And then yeah, like it's like Frobenius distance squared, but like the penalty factor for like this entry is the reciprocal of this guy.
So your prior though is like the basis of sigma, in which the eigenbasis of sigma in some sense.
Kind.
You're preferring that you would.
This is only so I can like easily state to you the definition of chi-squared. So what you actually do is like first you just run your like L2 squared error algorithm on rho, and it gives you back some matrix. And then In the same way, in the classical case, you like renamed the outcome so that Q1 is bigger than Q2 is bigger than Q3. You're like, oh, to make my life simpler, I'm just going to rotate space so that my current estimate becomes like a diagonal matrix. And then you're like, oh, thank goodness I did that, because now I know the formula for chi-squared divergence between a diagonal matrix and the unknown matrix. It's kind of this Frobenius thing. Somehow I feel like that didn't answer your question.
Well, I just wanted to, didn't care about the algorithm, just the definition of the chi-squared.
Yeah, it's like somehow, it's like an L2 squared or Frobenius squared, like how well does rho compared to sigma? But there's some penalty factor where like, yeah, like you have different penalties for how well rho is looking with respect to the eigenbasis of sigma. Yeah. So that's it. The summary is, one thing we did is you can do quantum state estimation to this ridiculous level of closeness with the same sample complexity as for the previous known algorithms that only got super closeness. And as a consequence, we got this quantum mutual information tester with basically linear dependence on the accuracy, which is good. And open problems are, one is like, this problem only came to me after we wrote this paper, but like I wonder if there's like a simple algorithm for quantum state estimation with L2 squared error. See, I think people never cared about it or tried it before because like L2 squared error, like in the classical case, it doesn't inherently have a natural meaning. You never like actually care about it. You only use it as a tool to analyze some other distances that you do care about. But it is the easiest one, so like maybe there could be like a simple algorithm. I would like to know. And the other one question is, Steve and I tried to get like extend this mutual information tester in the quantum case to a conditional mutual information tester. And that was like a lot harder because there's a funny thing with conditional mutual information. In classical case, the mutual information is non-negative. That's not hard to prove. And the conditional mutual information is just like the expectation of some mutual information. So it's also non-negative. So that's fine. But like that's not the definition in the quantum case. The quantum case, you can only define it as some difference of entropies. And then it's not even obvious that this quantum is non-negative. And in fact, it's like an extremely difficult theorem that like quantum conditional mutual information is always non-negative. So it's hard to even like know that this quantity is non-negative, let alone test if it's 0, let alone get a robust characterization of when it's 0, which is kind of what you need to do here. So we got stuck, but maybe we can solve it later. And
can you say what just like more precisely what the problem is?
yeah, in fact, it can even be over 3 bits. So I give you copies of an unknown state rho on 3 qubits, A, B, and C. And you want to get copies of them and do some measurement. And you want to accept with high probability if the mutual information of A and B conditioned on C is 0. And you want to reject with high probability if the conditional mutual information between A and B conditioned on C is bigger than epsilon. And you want to do it with like 1 over epsilon-ish many samples. And what makes these things hard is like to estimate the actual mutual information or conditional mutual information, you need quadratic dependence on epsilon. But here we're not asking you to estimate it. We're just trying to tell like, is it 0 or is it far from 0? And that's easier. In the same way to like estimate the bias of a coin flip to epsilon, it takes you 1 over epsilon squared samples. But if you just want to tell, is the bias 0 or is it epsilon, you can do that with 1 over epsilon samples. Same kind of phenomenon. OK, and that was indeed my last slide. So yeah, thanks.
Does anything simplify if I give you an additional information that the quantum state is pure?
Oh, does anything simplify if I give you the information the quantum state is pure? Yeah. So actually, all these problems, you can get like better dependence as a function of the rank of the state. So like, for example, just for the problem of like learn an unknown state, I said it requires d squared over epsilon copies. But you can actually do with like d times the rank over epsilon many copies. So if it's a pure state, you actually only need like d over epsilon copies. And if it's a low rank state, it's also order d over epsilon copies. Yep.
So maybe I didn't understand the Markov chain part. In that case, what is the amount of time you need to compute? So what is the compute time of this?
Oh, OK, 2 things. That was about the Markov random field on the tree thing. First of all, we don't even, in the quantum case, we didn't even solve it, so we don't have anything. But the classical papers, they have like, if they're like n vertices, there's sample complexity is like n over epsilon. The time is like n squared over epsilon, I think. Is that answering your question?
Okay, so in the quantum cases,
The quantum case, we don't even know how, we can't prove anything. Yeah. I mean, we're hoping to prove like a similar result, but we got stuck. So, yeah.
Okay. I'm not an expert in probability, but I heard that in some other like quantum things, sometimes people introduce an extra bit and then do some like operation, and then kind of like maybe that would like make it easier for you to like estimate. Have you ever thought about that? Like introducing an extra qubit or extra pure bit?
Yeah, this I'm not sure of exactly, but one thing that is maybe related to your question I can mention, which is I think for a lot of these learning algorithms, if you were ever to try to use them in real life, you would care a lot about like how complicated is the measurement the quantum algorithm has to do. And the algorithms I talked about here were like assuming your quantum algorithm can do like entangled measurements on the entire state, which is actually very, like all the copies of the state, which is very unrealistic. And there's a lot of work on what can you do if, when you get your copies of the quantum state, you have to do a separate measurement on each of them. Because this is like a simpler class of things you can do, but it's like more realistic. And you get like worse results, like worse bounds, but like maybe it's a simpler algorithm in real life. And one nice thing about our algorithm that's like a reduction from kind of like L2 squared learning to chi-squared learning is it doesn't change whether your algorithm is like, it preserves single copy measurement algorithms. So if your L2 squared algorithm like only measures the states one at a time, then like this chi-squared algorithm will also only measure the states one at a time. So like you can equally like preserve this factor when you plug it in. I'm not sure that exactly answered your question, but.
Oh yeah, maybe like I was just trying to mention like maybe if like you increase dimension to have like one more slot to store things, and like if you have some other like unitary matrices applied to that, maybe like can bring some previous information to the newly added bits, and I don't know, like maybe that just.
Yeah.
But
it could potentially. I guess the known lower bounds that say these results are tight, like apply even when you're allowed to add more qubits. But I think, yeah, this also maybe gets at the space complexity of the algorithms, which we didn't study very much.
okay, that's fine. Thank you.
Any other questions?
Okay.
Is it?
Oh.
So for states where you might have like an area law of entanglement, can you get a better scaling with this condition?
Yeah, great question. So all these results, indeed, were about like try to learn an unknown state or probability distribution, like making absolutely no assumptions on it. And first of all, maybe that's like overly ambitious. Like maybe you could always assume some things about your state. And maybe you want to do this too, because like these all have a dependence that's like on the number of outcomes, d, which is like polynomial in d. And if you have 50 qubits, then d is 2 to the power of 50, and so then it's like infeasible. Same if you're trying to learn a probability distribution on 50 bits. You don't want to try to like output the whole distribution as a table. So yeah, there's a lot of interesting questions about like, let's make a hypothesis or like a model for like a limited class of distributions, like they satisfy an area law or they come from a graphical model, and try to get much better sample complexity. And yeah, we didn't solve anything about that in this work, but like this is definitely an important range of problems to think about.
Is it possible to say like a sentence or two about what representation theory shows up?
Oh, what
in the
representation theory shows
representation theory and then more?
Yeah. Let's just try to say you're like learning a classical probability distribution. There's two symmetries at play. There's this SN symmetry because you get n IID samples. So like if somebody came and permuted your samples, you wouldn't care. It shouldn't affect your algorithm. And there's also like some SD symmetry because you don't actually care about the names of the samples. If somebody permuted the names of the outcomes 1 through D, you still wouldn't care. And so even in the classical case, you could get all representation theory on it and get into the representation theory of like Sn cross Sd. And it seems not effective to think about algorithms this way, but you could. And the quantum case is like similar, except the second, you still have the Sn symmetry. The second symmetry is like the symmetry of the unitary group in d dimensions, because you don't kind of care about like rotating these eigenvectors. But somehow there, like the only way we knew how to design algorithms involved looking at how the tensor product space, CD tensored n times, which is where your samples come from, how it decomposes given the representations of the unitary group and the symmetric group. Yeah.
Last chance. Any questions? Okay. Let's
Okay,
start,
thank
Ryan.
you.